So here we go, the final section of the syllabus, all about making fertilizers. In particular, we're going to look at how ammonia is made, because most fertilizers are based on ammonia. So the purpose of fertilizers is to help increase crop yield by supplying important nutrients to the soil, in particular nitrogen, but we'll also look later at phosphorus and potassium and what they are needed for. So most contain nitrogen and they are mostly made from ammonia, and ammonia is made by what's called the Haber process. This is a reversible reaction and it was developed quite some time ago, probably during the First World War, and if you get a chance, please have a look on Wikipedia at Fritz Haber's story. It's actually quite interesting. The raw materials are air, which provides the nitrogen in ammonia, and natural gas to provide the hydrogen. What you have to do is purify the nitrogen and hydrogen before reacting them together. If you don't, then this will spoil the catalyst that's used, and they're reacted together at a high temperature and high pressure. The specific nature of those temperatures and pressures we'll discuss a bit later. Now, the reaction is reversible, so that means that ammonia also breaks down into nitrogen and hydrogen as well. So we have to control the conditions very carefully to make sure that we get as much ammonia as we can, as quickly as we can. And you'll notice there that the reaction is exothermic. And you'll notice the reversible sign. So in a closed system, this will become an equilibrium when we allow the forward reactions and backward reactions to come out at the same rate. So ignore that piece about the worksheet. We would be doing that if we were in class. It's just a little simulation where you can change the pressure and temperature to find out what the best conditions are. But just have a look at the equilibrium and use your ideas that you know already about Le Chatelier's principle and do some predicting about the temperature and the pressure. Okay, just pause the video briefly and do that, please. So if I increase the pressure, the equilibrium will try and counteract that increase in pressure by moving to the side with the fewer number of molecules. There are 1 + 3, 4 molecules on the left hand side, 2 on the right hand side. So this is the side with the fewer molecules. So if you increase the pressure, the equilibrium will move to the right and you'll make more ammonia. Now what about temperature? The reaction is exothermic. So if you increase the temperature, the equilibrium tries to reduce the temperature by moving in the endothermic direction, which is backwards in this instance, so breaking down ammonia. So there's a problem there if we use a higher temperature, or too high a temperature I should say, in that it won't favour the amount of ammonia, it will break them down into nitrogen and hydrogen. So there's a little problem here, because if we use too low a temperature, the rate will be too slow, because you have to try and get as much as you can, as quickly as you can. So just have a little think about that diagram. You don't have to print it out to complete it, but you can if you really want to. So pause the video and think about what your answers might be. Okay, so natural gas makes hydrogen, oxygen mainly plus some other gases are removed, leaving mainly nitrogen. You then get rid of CO2 as well. Then you take nitrogen plus hydrogen, and the unreacted gases are recycled. Because under the conditions that we use, you only get about 15% of the nitrogen and hydrogen converted to ammonia. So it's important you save money by recycling the nitrogen and hydrogen again. To get the nitrogen and hydrogen separated from the ammonia, the mixture is cooled. Ammonia condenses as a liquid and is collected wherever, cylinders, and the nitrogen and hydrogen are recycled. Easy bit here, nitrogen plus hydrogen, reversible reaction ammonia, and then you can complete this symbol equation as well, N2 plus gaseous plus 3H2. So you'll have to go online on the version on Google Classroom to have a look at this video clip. It's just gives you an idea of an ammonia plant. If you've ever been up the A19 up towards Scotland, if you go past Billingham, which is a bit north of Middlesbrough, there's an ICI, or used to be an ICI ammonia plant there. You can notice it perhaps best if you're coming south on the A19 just before you come to Middlesbrough. So what conditions are used in industry? Well, the temperature used is between 400 and 450 degrees centigrade. The pressure used is 200 atmospheres, and the catalyst used is iron. Now, there's a 6-mark question in existence, but you're probably not too worried about that, to explain fully why these conditions are used. Pause the video now if you want to have a think about how you might get 6 marks for this. It revolves around Le Chatelier's principle. So the temperature, 400–450 degrees centigrade. If we use a lower temperature than 450 degrees centigrade, then the rate of reaction is too slow. And unfortunately, we won't make ammonia quickly enough. If we use a higher temperature, then the reaction is exothermic, so using a higher temperature will cause the equilibrium to shift in the endothermic direction, and the ammonia will break down into nitrogen and hydrogen. Pressure, in theory, we want to use as high a pressure as possible, but we use 200 atmospheres. And again, this is a bit of a compromise between rate and yield. If we increase the pressure, we'll increase the rate of the reaction and increase the yield. Unfortunately, increasing the pressure is very, very expensive, so we use a bit of a compromise, 200 atmospheres, 200 times atmospheric pressure, that is. And a catalyst is used. Iron is the catalyst chosen, and that speeds up the reaction. They usually use a catalyst with quite a big surface area. It speeds up the forward and backward reaction by exactly the same amount. So putting those into sensible sentences would get you 6 marks. So, simple set of questions for you to have a think about and prepare your answers. So pause the video now while you prepare your answers. Okay, number 1, simply N2 gaseous plus 3H2 gaseous, equilibrium sign 2NH3 gaseous. Number 2, what happens to the yield of ammonia if we increase the pressure? The yield will increase. The yield increases because the equilibrium moves to the side with the fewest number of molecules. What happens if we increase the temperature? Well, the yield decreases because the equilibrium shifts in the endothermic direction, which is the backward reaction. And what happens to the yield of ammonia if we use an ion catalyst? Now this is a slightly difficult one to understand. The actual amount we make does not change, but we just make it much quicker. What are the conditions used for the Haber process? 450 degrees centigrade, 200 atmospheres. And what is the yield of ammonia? As I mentioned, it's between typically 15 to 20%, but 15% is the answer that is usually accepted in exams. Why are higher pressures not used? Too expensive. Why are lower temperatures not used? Because the rate would be too slow. Okay, so it's not just nitrogen that's used for fertilizers. We also need phosphorus and potassium. Phosphorus P, potassium K. And if you know your biology, you'll know that plants require both phosphorus and potassium for healthy growth. I'll leave that to Mr. Fraser to explain though. So these NPK fertilizers are mixtures of compounds to give the correct ratio of nitrogen, phosphorus and potassium. These are an example of a formulation. Many NPK fertilizers contain ammonium nitrate. How might ammonium nitrate be made? Have a little think. Okay, ammonium nitrate is made by reacting ammonia with nitric acid. Please remember ammonia is the compound, but it's the ammonium ion when that ammonia reacts with something else to make a new compound. How is nitric acid made? Well, the long and the short of this is that it's made by catalytic oxidation of ammonia. And on the next slide there's a little video. Again, you'll need to go onto the online version on Google Classroom to watch that video showing how nitric acid is made. You don't need to know any more details than catalytic oxidation of ammonia. So, where do we get potassium from? Remember, it's not the element potassium, it's potassium compounds. So basically they have to be dug out of the ground. You can find potassium sulfate and potassium chloride in the ground. You can also actually obtain potassium chloride from the sea. Calcium phosphate, again, this is found in rock formation, in phosphate rocks, and is made by reacting these phosphate rocks with phosphoric acid. And phosphoric acid is, strangely, made by the reaction of nitric acid with phosphate rocks. So there's a little bit of a circular issue there. And that then is actually everything you need to know. Okay, there will be a test on this topic. That test will give you the last opportunity to enhance your predicted grade, and that test will take place with a week's notice.